All right, so we've been talking about circular motion, and what better way than to look at this wheel to kind of give you a better idea of what's going on. So we've got two types of speed that we've been talking about. We've got our tangential speed and then our angular speed. Okay. Angular speed has to do with how quickly it can revolve, right? It can get around that circle. Does that make sense? All right, so it's really dependent on how quickly it can go through that 2 pi radians. All right? So if we look at these two spots, they have a different radius, but all we're going to look at when we talk about the two speeds of this thing in the angular direction, angular speed is how quickly, all right, do they pass, like, say, this point at the top each time they go around. Okay? You'll be able to see it. So if we look at every time it passes through the top, what do you notice about the angular speed, just looking at the 2 points? Right? Make sense? Can you see it? Right? So what do you see? What can you say about the angular speed of these 2 points? They're the same, right? So if I just spin the two, where the two points are, okay? So we see that, right, angular speed, and we've already kind of seen that with the work we've done, is that it's not dependent on the radius, right? It's just dependent on the amount of time it takes to go around. And in this case, they both go around, they hit the same point angularly at the same time, and they're going around the same amount, right? The same circle. Does that make sense? Or I should say like the same angle, 360 degrees. Okay? But if we now talk about tangential speed, which is that speed, it travels this way, right? 90 degrees to the surface, right? That is dependent on how far away you are from the center of the circle, right, or from the axis. So now if we look at who is just traveling more quickly between these 2 points as it travels around, all right, what do you see? Which one seems to be traveling around the circle more quickly? The top one is tangentially?
Yeah, tangentially. Wait, I thought that...
Yeah, because V equals WR.
Omega R. Yep, so all right, or if we think of V equals 2 pi R over T, correct? We think of 2 pi R over T. The outer one, right, it's got a larger radius, so it needs to travel faster to travel the same distance as the lower one. Does that make sense? All right, to get around the same amount of time, it has to travel that larger circle, the larger circumference, more quickly. Okay, so it's kind of cool and kind of weird at the same time that you can look at this thing in 2 different points of view and get 2 different answers, even though it's doing the same thing. Right? So hopefully that kind of opens you up a little bit in terms of what we talk about when we talk about speed in the circular motion. Over here. There we go. So now, this is really simple. It's very quick. We talk about analogous equations. All right. So you may have seen already in your notes, in the reading, when we talk about the equations, and analogous means that we have things that are similar to each other. All right, they're just talking about 2 different things, but they're very similar. Okay. So typically, when we've talked about kinematics, we've talked about distance, right? We've talked about speed, and we've talked about acceleration. Correct? Okay. So we've talked about distance, speed, and acceleration when we've talked about our kinematic stuff. Okay? Things along in a straight line or in 2D motion. We also have, they have analogous counterparts when we talk about circular motion. Right? Instead of distance, right, how far we are from one point to another, we have our angular displacement. We call that theta, right? The angle that the object traces out as it goes around that circle. Okay? We also have then, we've got our speed, our tangential speed. Well, when we talk about the speed in the circular motion, we have our angular speed, right, omega. And we have our acceleration, but when we talk about angular acceleration, it's now alpha. Okay?
So we kind of just
Alpha.
give them Greek letter names.
Yeah, that's how we tell them differently, is by, just make them Greek. That way we know we're talking circular. It's not even something completely different. Okay? Well,
So is that the centripetal force, or is that the...
there's no force here at all.
So is it centripetal acceleration, or is it acceleration?
This would be centripetal acceleration.
Okay.
This is the angular acceleration, or how quickly its speed as it spins is turning.
Okay.
It's changing. Okay? So now let's look at some equations that we know. We know that v equals d over t. Right? Very simple. If we put this in terms of circular motion, and it's analogous equation, it would be omega equals theta over t. Okay? The slight little difference is typically your t here, we talk about period, the time it takes to go around once. It's still time, it just has a slightly different definition. Okay? We can kind of flesh this out a little bit more, right? We know that, actually I'm going to skip that part for now. If we look at our kinematic equations that we know, right, we know that x is equal to x sub o plus v sub o t plus 1/2 a t squared, right? If we're talking circular motion, that becomes theta equals theta sub 0 plus omega sub 0 t plus 1/2 alpha t squared. Okay. Let's say we have v sub f squared minus v sub o squared equals 2ad. Will, what do you think that would be?
Angular speed s squared minus angular speed original squared is equal to 2 alpha theta.
Yeah. Good. Okay. So we've got omega sub f squared minus omega sub o squared equals 2 alpha theta. Okay. Makes sense, right? Okay. So again, we're talking about similar things, but instead of talking now in terms of 1 and 2D motion, we're talking about circular. So all we're really doing, all the laws still apply. We just now change them from d to theta, v to omega, a to alpha. Okay? So it makes sense. So if you're ever stuck and you need an equation, you can go back to your kinematic equations and just substitute in what you know about kinematics and substitute in the circular pieces, and you're good to go. Okay? All right, so we know that v equals d over t, correct? Okay. This is awesome. So let's say I want to know what v equals the relationship between omega and v. Okay. So I know v equals d over t. If we're traveling in a full circle, what would we call that, or how would we represent that? 2 pi r, right? 2 pi r.
Yeah.
That would be the distance that the object travels, right? Or you could say, yeah, you could say 2 pi radians times the radius and then divided by t. Correct? Okay. Now, we know that 2 pi radians over t is what? What would that be? 2 pi radians, so it's 360 degrees around, divided by the period would be what? Not tangential speed. Angular speed. Were you going to say that, John? All right, so this piece right here is our angular speed, right? Because angle-wise, right, it travels around 2 pi radians, and it takes this period t to get around there. But you notice that when I spun the wheel, the tangential speed, that radius matters, right? How far away the point is from the axis. So we need to take that radius into account. Okay? John, you good? All right. So we know then that v is equal to omega r. Similarly, the acceleration is equal to alpha times r. Okay. So the book told you that the centripetal acceleration is v squared over r, right? So remember, centripetal acceleration, it's not how its speed is changing. Centripetal acceleration is how its direction is changing, right? So this acceleration does not change its speed, the object speed. It changes its direction, okay? And remember, centripetal means center seeking. So it's always pulling the object towards the center, all right? And there is no such thing as a specific centripetal force, all right? It's just something that we call, it's a force that we name that's pulling it towards the middle. So it could be tension in a rope, right? It could be, like if you throw a softball, it could be your arm as you pull the ball around and throw a pitch, okay? So it could be friction if you're driving around a turn, right? Those are all examples of centripetal forces, right? But there's no actual thing called centripetal force, right? Just as there's no such thing as centrifugal force, right? Force that pushes you away from the center. A centrifugal force is actually just a lack of a force. All right, so that means there is no force, and that means you feel like you're moving away from the center, but there's actually no such thing. Roshan?
You said for v equals omega r and then a equals alpha r.
Mm-hmm.
You also say d equals theta r.
Yeah, you can say d equals theta r. Yep, good. So we know that v is omega times r. So if we plug that in up here, we know then that omega times r squared divided by r. And then that is equal to omega squared r squared divided by r. Those r's cancel out. So another way that we can determine the acceleration, the centripetal acceleration, is if we do omega squared times r. Yep.
So if A equals alpha, how does it A equal alpha R?
A equal alpha r. So we could go through, do the same thing we did here, and we would find out, we would be able to make this substitution.
Understand what you did there.
Right here?
Above that.
This? Okay. All right, I'll come back to you. Okay. So we know that if something's traveling in a circle, angular speed-wise, that speed is determined by the amount that it travels around in radians, so 2 pi radians,
Right.
divided by how long it takes for it to go around. Okay? So this is the 2 pi radians, the distance it goes, and how long it takes to go around. This is your angular velocity. Okay? But this piece right here, this is the distance. If you're talking speed, remember it's distance divided by time. This is the circumference of the circle,
Right.
is 2 pi r. Right? But this 2 pi divided by t is the angular piece. The r is left over. Okay? Does that make sense?
Yes.
Okay. Tyler?
So in the talking about A equals alpha, but then you also wrote A equals alpha R. So are we just considering that those are simple?
Okay, so this is saying if you see an A, you can replace it with an alpha. This is the equation. If you want to find the tangential acceleration, and you know the angular acceleration, this is the relationship. Okay, does that make sense?
Yeah.
Okay.
So we're just kind of saying those symbols are related, but not necessarily always equal.
Right, so the things up here are just saying they're analogous to each other.
Yeah.
All right, cool.
How are you getting a equals alpha r?
A equals alpha r. I can do it out. I haven't done it out in a while, but we can do it out. You good? Okay. So are we good? So you can see the two relationships between the triple acceleration could be v squared over r. Could be omega squared times r. Okay? And if you want to find the force, remember that F is just equal to ma. And if we're talking centripetal, then the centripetal force can be m times v squared over r, or it could be m times omega squared times r, depending on what you have, okay, what you know about the situation. Okay?